Okay, so we saw that these two line integrals in this particular vector field ended up being 0. Remember that? So, and we call these circulation integrals. Circulation integrals means that you make a closed loop. You start and end at the same place without crossing. You never cross, and you come and you start and end at the same place. So these were circulation integrals, and so circulation integrals we'll often see like this. So it's our line integral. But then if it's a circulation integral, so over some path C, it's a circulation integral, you see a little circle like that. And that circle means you're going to start and end at the same place. So what we said was, why did we get 0 for both these? Remember why we got 0 for both these circulation integrals? Right, because the vector field was conservative. And what about that vector field was special that made it conservative? Okay, so Winston remembers. So you guys remember this? So because it was a gradient field, negative 2y is actually the partial derivatives. Negative 2 is the partial derivative with respect to x, and y is the partial derivative with respect to y for a particular multivariable function, which makes it a gradient field, right? And so we said that gradient fields are, we said, conservative. So you think of it like the conservation of energy. If when you make it around the loop, energy is conserved, right? And so like the net result is 0, like if it's work, okay? This is a force field and we're traveling through a force field, then the net work that the force field does is 0, so energy is conserved, okay? And so that means and so what that means is all circulation integrals in such a field, what can we say? Equals 0. So any circulation path that you pick doesn't have to be these nice easy ones. Doesn't have to be centered at the origin. So if I make a circle like this down here, a loop like this, start and end at the same place, it can be anywhere in the field, and if I do the circulation in that, calculate the net work around that loop, it's going to be 0 if I'm in a gradient field, because gradient fields are conservative. So that's just a kind of a overview of where we left off last time. Make sense? Any questions on that? So that's just a little catch up and review. Okay, so then let's take that a step further. So I'm in the same field. And I want to look at going from, say, 3, 0 to 0, 3 up there. I'm in the conservative vector field, and I'm going to go, say, from 3, 0 to 0, 3, and I call that my path C. So what can you say about, what would you say about that line integral? I'm in this conservative vector field. I'm going from 3, 0 to 0, 3 along C. What would you say about that particular line integral? Equal to 0? Why not? Why no?
It's not the whole path.
Yeah. So it could be 0, but it's not just a guaranteed it's 0, because why? Because it's not a circulation integral. I'm not going around in a loop and ending up where I started. Okay. So we look at this, and so some of you said then you would predict, what would this be? Positive, right? Because so along the way, the general direction of the vectors is generally in the same direction as the path, or components of those vectors are in the direction of the path rather than against the path. And so we would guess this is positive. And I'm going to tell you, and you could easily find that. You guys are expert at calculating these. I'm going to tell you that it's equal to 10.5. Okay, because it is. And we could do that, and we would get the answer that line integral has a value of positive 10.5. Okay, so now I want to do this line integral from 0,3 to 3,0. I'll call this so I'll call that one C1, and now I want to call this one C2. So I want to calculate the line integral C2 along the straight line path back from 0,3 to 3,0. We want to calculate that. We actually want to get its value. I'm done. Anybody else done? Raise your hand if you're done, if you got the value of that. Let's see. Hem, what do you think?
Zero.
C2 is 0?
Oh, sorry. Oh, I thought you were
No, C2. The C2 starts here and ends here along the blue straight line path.
Negative.
Negative what? I want the value. We're going to calculate it. I want to get the value. Yeah. Negative 10.5. What do you think? How do you know that?
Because it creates a circular path.
That would finish a loop, right? It would finish a circulation. So if it's positive 10.5 to get from 3,0 to 0,3, and we know if we head back and we get to where we started, that we know that net work or that circulation has to be 0. Therefore, back from C2 to C3 has to be negative 10.5. Okay? Here's another path. This two line segments here, C3. Okay, what about that line integral? Okay, that's the question. Who said that? Which way is it going? So rather than going back, I'm gonna do the same thing I did for C1. So I'm gonna start at 3,0 and go to 0,3. Who's got that one? What's that worth? Ryan.
7.5.
Why?
Because it starts in the same point and ends up the same direction.
Okay, so if I was going in the other direction, if we were going back this way, we know it would have to be negative 10.5. If I just go in reverse along the exact same path, then it has to be the opposite. So this leads us to another conclusion. So what about this? So this is C for C crazy. What's the value of that one? 10.5. So this then, so if I start at 3,0 and I end at 0,3 along any path, that the value of that line integral is going to be 10.5. This is called path independence. So conservative vector fields are meaning if you have the same start and end point, right? You have to have a fixed start and ending point. Every path from the start point to the end point will have the same value of the line integral in a conservative vector field. And that comes out of the fact that if you made a loop out of two of those paths, if you made a loop, it would be 0. So one of them would have to be positive, the other would have to be negative, right? So that we get it kind of, that path independence idea comes out of the fact that looking at loops. and then going backwards on half of the loop. You go backwards on half of the loop, you're going to get the same value that you did on the other part going forward. Okay. So what do we know so far? So gradient fields are conservative. That means every closed loop in a field will be 0, and you have path independence given any two, given any starting point and ending point, any starting point and ending point. Every line integral with that start and end point will have the same value, path independence. So let's look at no way. Something is not happy. What's going on here? Okay, so we're going from I'm going from 1, 0, so you gotta just, these all will coincide here at the end at 1, 0. 0, 1, I mean. So all come together at 0, 1. And then down here, 1, 0. And I want to go this way. And I got C1 is along the unit circle. C2 is along the straight line segment, and C3 is along y minus radical x. And they all go from 0, 1 to 1, 0. What about the values of these line integrals? What do you say about the values of these line integrals? He wants equal to each other. So is it a gradient field? So this is the field. This field. This is, I guess I'm calling this field 1. And it's negative x, x. But before we even analyze that, let's just look. If you were just predicting, eyeballing, go along C3. Do you think that's positive, negative, or 0? Negative. Now look along C1. Positive, negative, or 0? Same amount negative or more negative? It's looking like more negative, right? So we've got definitely vectors. We're encountering vectors with much greater magnitude along C1 than C3. So does it look like the line integral for C1 is going to be the same as the line integral for C3? No, more negative for C1. And so why is that? So that would indicate we don't have path independence, which would indicate it's not a gradient field, right? So negative xx is not a gradient field. It's not conservative. So that means this different paths from the same starting point to ending point can have different values. Okay, so I want to show you, so far, in order to determine if a field is a gradient field or not, we kind of like pretended it was and tried to find the function, right? We tried to find the function who had those partial derivatives. So I want to show you a different way, a quicker way to maybe make an initial check as to whether you have a gradient field or not. Do you remember, back when we were doing partial derivatives, something called Clause's theorem? You had some web work. I think I mentioned it briefly in class. But so what are we saying? We're saying this is the partial with respect to x, maybe, right? And this is the partial with respect to y, maybe. And we saw a relationship of second derivatives. Remember this? What was the relationship of second derivatives? Right, that the second with respect to x and respect to y was equal to the second with respect to y and respect to x. So we can use this as a check to see if you have a gradient field or not. So what would we do? We'll take this one and do what? Take the partial with respect to y. Because if this were the partial with respect to x, then that would be like the partial with respect to x and then y. So what do we get with respect to y? 0. And then this, if it's a gradient field, this would be the partial with respect to y. So we're saying, again, this is all question mark, right? This is all question mark, okay? This would be the partial with respect to y. What should we do? Take it with respect to x, right? We're going to find this value, and what's that? What's the partial with respect to x? 1. Conclusion? Not equal. They're not equal, right? So because they're not equal, it's not a gradient field. It doesn't, because this was always true, given us starting with a multivariable function of x and y. If you take this partial, this second partial, and this second partial, they'll be equal. So supposing that this was the partial with respect to x, and this is the partial with respect to y, taking those, getting those second derivatives, if they're not equal, Clause's theorem doesn't hold. And we can go back and say, well, those weren't partial derivatives in the first place, right? Those can't be partial derivatives with respect to x and y in the first place, not a gradient field. So that's a different way to kind of analyze this, rather than just trying to find the function and saying it, you can't. Both are very important, okay? Does that make sense? Okay, so we don't have path independence. Is there any questions on that? Does that make sense? You guys good? All right, so we don't have path independence. So if that's the case, then there must be ways to get all those paths from 0, 1 to 1, 0, we said were what? We went this way? Along those paths? All negative, right? Starting here, so call this point A, from A to B. So what I want you to do is I want you to I'm going to take attendance. While I'm taking attendance, I want you to find, in this field, I want you to find at least 2 more paths that give a 0 line integral from A to B, and at least 2 more paths that give a positive line integral from A to B. Just to underscore that we do not have path independence. From A to B, you can find line integrals that are negative. We've already found 3. You can find line integrals that are 0, and you can find line integrals that are positive. So as you start looking at it more and more, the creativity starts to flow. You'll be able to find that there's lots. So you can find ones that are positive and find ones that are 0. Okay, and then work on that, and then discuss that among yourselves. So we're going from A to B, and you're looking for paths that you would know are positive and paths that you would know are 0. Winston's got one. Tell me.
So you can kind of go down the x-axis, and I won't really give you any change, and you can just like move around to B. It'll give you more positive effects.
So you want to start at A and do what?
Go like straight down a bunch, and you loop back up to B.
How far do I have to go down?
I don't know exactly.
If I go down here and go across like that?
No, first you have to go below.
Okay, go below.
And then if you like wrap around up.
So like do like wrap around like this?
Yeah.
Because I'd get some negative, but they'd be lower magnitude, and then higher magnitude positive here.
Yeah.
Yeah, so that works. So you can come all the way down the y-axis and then kind of make like a half circle around like that, and that'll be positive. Because the first part of that you'll have negative, but it'll be small, then you'll have big positive at the end. Okay, another positive. Yeah, go ahead.
I was thinking about going very far left from where you start at point A.
Yeah.
And just
This?
Yeah, and then move diagonally downwards and just follow those vectors.
Okay.
And then afterwards do a similar path to what Ray said.
Okay. Yep. So you got some negative here. We got to make sure that positive or is bigger than that negative. Okay, another positive. Yeah, Andrew.
Move above me in the fourth quadrant as we not take any negative and then move directly into negative x.
Are you saying go like this?
Yeah.
Yeah. So if you had it at a 45-degree angle here, so this all would be 0, right? And then through the fourth quadrant, all positive, and then through the third quadrant, all positive. Through the fourth quadrant, 0 again. See that? Okay. How about 0? Somebody new. Ada.
Down the x-axis to like negative.
Y-axis.
I mean, yeah, y-axis.
Okay. Down the y-axis.
To maybe negative 0.8 and then up to b.
Negative
So those would be
0.8. Oh, okay. So don't go all the way to -1. So go somewhere like to here, and then straight like that.
Yeah.
That'd be. Oh, no, go to 1. So okay, so go all the way down. That'd be 0. So it'd be actually have to go to -1, and then orthogonally across like that. Yep, all the way down to -1, then straight to b. That'll be 0. Another one. Yeah, Ryan.
If you go from A to the point -1, 0, so
Okay.
to the left, all those vectors are going to be perpendicular, so they don't contribute.
Right.
And then if you go across the x-axis to point B, you're going to get the vectors mirrored but in opposite directions. So
Yep.
it's a lot.
So then you have a positive contribution there, but then the equal and opposite contribution there. Yeah, so you could go diagonally down to -1, 0, and then straight across the x-axis. Okay, so again, just highlighting the fact that in a non-conservative vector field, given the same starting and ending point, it's possible to have line integrals that are negative, positive, or 0. Okay, so let's go back to, let's look at 1y. What about 1? So this was negative xx. How about 1 comma y? What do you think about that? This is F2 now. Is 1 comma y conservative? Well, let's do the Clause's theorem check. If we do the Clause's theorem check, what do we do to this? Derivative with respect to y, meaning xy would be equal to 0. And this one, we're going to do the derivative with respect to x. It is. We got a match. Conclusion? Gradient field, conservative, right? Gradient field, conservative. And so if I go from point A to point B, say along C1, what do you think? Positive, negative, or 0 along C1? That's the unit circle. What about the beginning? Positive. What about through here? 0-ish, right? 0-ish. So you got definitely positive and then 0-ish. Conclusion, C1? Positive. Okay. Big positive or little positive? Just like slightly, right? Because you just have a little part here where, a component of these vectors is positive. So we're thinking it's a small positive value. So that would, if this is a conservative vector field, then we have path independence. That means all three of these line integrals from A to B should have the same small positive value. So does that check out? If we go along, say, C3, does it look like a small positive result? So what happens at the beginning? A little bit negative, right? Actually, you see that these are, it's like a little, vectors are going this way. So that's a little bit negative through the middle, 0-ish. But then starting here, this whole thing, positive. So that positive part is overtaking the little negative contribution we had at the beginning. And we would expect, again, a small positive value. Because this is a gradient field, 1y, all those line integrals from a to b will have that same small positive value, including all the paths you dreamed up from a to b through the second, third, and fourth quadrants. No matter what you did in the previous example, all those line integrals will end up having the same value because you have path independence. Okay, does it make sense? Any questions? All right, so how about this? Let's do a line integral through this field. So here's the surface. Let's see here. Okay, and so where are we going from? We're going from where these points are. Just look. That's a better view there. Okay, so we're going to start at point negative x and y are negative 0.5, negative 0.5. And then whatever the function value gives us, okay? And then the final point is going to be at positive 0.85 and positive 0.65. And then whatever the function, the z value is. So those are just the x and y coordinates of those. Okay, and so I had that right there. All I had to do is that. So Frodo and Sam have a combined mass of 75 kilograms. So they're starting here, and they're going to make their journey to take the ring from there to the fires of Mordor. And Sam says, I can't carry the ring, Mr. Frodo, but I can carry you. Okay, so they're going to make their journey. And so I want to, and that's through this force field that they're going through is a gravity field. So F of xyz is the gravity field. And assuming, which would be 0, 0, and what's the force of gravity? If G is so the gravity field is 0, 0 minus mg. Force of gravity is m times g. And so the question is, along the path, call it path M for Mordor. Along the path M, how much work does the force field do on Sam? Or what is, in other words, what is the line integral from negative 0.5 along this path M to 0.85 and 0.65? And then did you write the function down? There's the function. So we need to find the work along that path from negative 0.55 to 0.85, 0.65. Can we do it? Can we do it easily? how can we figure that out? How can we get the work to go from negative 0.5, negative 0.5 to 0.85, 0.65 along this path, along this awful Mordor mountain?
Can you just do the straight line?
Was that a stretch or a hint?
That was a stretch.
Okay.
Or, she said what I was
She's okay, that's what I was going to say. Go ahead.
Yeah, so since it's a conservative field, we can do a straight line and then it's equal.
How do we know it's a conservative field?
We can check. But it's a gravity field, so.
So is there some function? Now this case it's a 3-variable function that has that as its gradient.
Yeah.
What would it be? Negative mg z, right? Partial with respect to x is 0. Partial with respect to y. Partial with respect to z minus mg. So it is conservative vector field, and conservative vector fields are, what did we find out today? Path independent. So we're not going to use this path, right? Very wisely, we're not going to use that path. Instead, we can do the easiest path we can think of, which is straight line. Let's see, where's straight line? So straight line. Does that show up, the straight line? Oh, good. Okay, yeah. Think. So the work that the field would do on Sam as he carries Frodo, if they were to travel that path, would be the same work as if they're clambering on the mountain, right? So let's do it. Here we go. So we're gonna find the work is what? The integral. So we'll do S for straight now. So we got M is the actual path they walk, but because they're walking through a conservative field, we can do the path S for straight. Or let's do, maybe L is better. Let's do L for line. Capital S will stand for surface down the road here, so let's use L. So rather than using path M, we can use path L. And so we're going to do F dot dr. That means we have to do what? We have to parameterize L, right? Okay, remember how to parameterize? We got a straight line segment from negative 0.5 to negative 0.5, or the blue point to the red point. And I want to parameterize that. Remember our... Yeah, so let's do it so we do 0 to 1. So when we're writing this, or eventually we write the line integral, we want to write from 0 to 1. So that... Remember how to do that? So remember, you start with if our parameter is 0, we want to get this point, negative 0.5, negative 0.5, and it ends up being the z coordinate of that point ends up being, I can't read it. 0.01, thank you. 0.01, that's right. Oh, it's right there. Negative, so we're going to go negative 0.5, negative 0.5, and 0.1. And then remember what I said? So then when t is 1, we want these to add together so that we get the final value, right? So then the coefficient of t will be the change, right? So how much change from negative 0.5 to positive 0.85? 1.35. Right, 1.35 t. And how much change from negative 0.5 to 0.65? 1.15? What are we doing? We're parameterizing the line segment because we need to write this whole single integral in terms of t. So we got to parameterize our path, which is a straight line segment. And then finally, how much does z change? 0.97. Good. Okay, so now we've got the parameterization. We can do dr in our head because they're all linear. That's easy. And so we can set up the work. The work is, and what is this? This is the work that the gravity field is doing on Sam, right? And then we know it's going to be from 0 to 1. And so F will be 0, 0, just a constant. And what is minus mg? So what's m? 75. They're little guys, right? Combined mass of $75 kilograms times, assuming the Mordor has the same gravity as Earth, 9.8. Is Mordor considered Middle Earth? Is that considered Middle Earth? Part of Middle Earth. And would it have lower or higher gravity than our Earth? We'll just go with the same. So 9.8, and then what? Dot dr, right? Dr is going to be 1.35. This is dx dt, dy dt, dz dt, dt. Is this consistent with the line integrals you guys have been working on? Are we good? First two terms are going to multiply to 0, so we're going to get 0 to 1. All we get is this third term, minus 7.5 times 9.8 times 0.97. Almost there. Okay, so what's this super easy integral? Antiderivative is that number times t, right? That number times t. And then it's going to be from 0 to 1. So in this case, when you plug in 0, you do get 0. So all we're going to plug in 1 for t, and we're going to get that number. So what is negative 75 times 9.8.097? Now something's wrong here. Why am I getting in the hundreds of thousands of joules?
The answer should be 712.95. Because it's just like that number inside there, 75 times 9.8 times 0.9.
Yeah, that's what I'm seeing too, but something's wrong. Okay, so would you negative 712.95? Let's go with that. Joules? And so what is that? That's the work that the field does on Sam, right? It's the work the field does on Sam. So how much work does Sam do? So the positive, right? So Sam does positive 712.95 joules of work. Oh, I know why. These are kilometers. These are all kilometers, and joules is Newton meters. That's why it's multiplied by 1,000. So these should be multiplied by 1,000 because these dimensions are in kilometers. Joules is Newton. So this is actually kilojoules. That's what this is, because these are kilometers. So let's just do that. Yeah, that's not nearly enough. Okay, that's better. Okay, so these are negative 712.9 kilojoules because those dimensions are in kilometers. Okay. So now there's another way to calculate work. All right. Potential energy of something that's up above ground level is, if you remember from physics, is mgh. Okay? So we can calculate the change in potential energy, which is potential energy final minus potential energy initial. So what's Sam's final potential energy? It's going to be mgh, which is 75 times 9.8 times 0.98. And what's his initial potential energy? 75 times 9.8 times 0.01. And if you do that, you get 712.955 kilojoules. Change in potential energy. So if you calculate the work done through the conservative field as a line integral bit by bit, so this is adding up the work bit by bit, it's the same as the change in potential. So there's a certain potential energy at the beginning, certain potential energy at the end, and that change in potential energy is the same as the work that you would do to get from point A to point B. What do you notice about that right there? Same as what? What's that the same as? It's the same as the potential function for this vector field, right? Why do we call it a potential function? Because in the context of work, it's like the potential energy. It's like the potential energy at a particular point. And so if you travel from one point to another, you're changing your potential energy, and that's the same as the amount of work you do. Okay, this is better than you think. Here we go. I know it's end of the day Friday, but so we could write the line integral can also be calculated how? So line integral along C of f dot dr could also be calculated. Instead of thinking of the potential energy, we think of this as what? The difference of the function, right? So it'd be like f final, what? Minus f initial. And how does this capital F vector field relate to little f? What is that? It's the gradient, right? It's the gradient field for f. And you look at that and you say, I know what that is. What is that? No, this whole thing. I told you it was better than you think. What is that? Look, I've got a rate of change function or a derivative function doing the line integral, and then I'm going to also be able to calculate that by the final value of the function minus the initial value of the function. Or the change, in this case, the change in potential energy is the same as the work done. Somebody, please. What is that? Fundamental theorem, right? So this is the fundamental theorem of line integrals. And it's basically exactly the same as the fundamental theorem that you know, right? Except now we're in vector fields, right? So now the derivative of a multivariable function is a vector field. And so the line integral of that vector field from point A to point B is the same as the value of the function at the final minus the value of the function at the initial. And so the best example here is with work and change in potential energy. So if you're doing a line integral, so here's the last big conclusion. If you're doing a line integral in a gradient field or a conservative vector field, you can actually parameterize the path and do the work to find the work, right? Do the work to find the work. Or you can find the potential function, evaluate it at your final point, evaluate it at your initial point, and find the difference. And that's the same as the value of the line integral.